Welcome everyone to our first webinar in Parkinson detection and machine learning. Today we're going to be talking about machine learning method for detecting Parkinson using vocal measurements. My name is Hassan Azzuddin. I'm a data science consultant in data meaning, and I'm a part of the enablement team. I have an applied data science experience in the healthcare industry, stock market, and retail. And I'm also a SnowPro core certified. I have implemented multiple machine learning models using Python and R for like more than 5 years in different industries. And as I've said, and for today's webinar, we're gonna talk about the Parkinson disease, the use case we're trying to solve, the data set available, and model with its results and evaluation metrics. So the Parkinson disease is a neurodegenerative disorder that affects dopamine producing within patients, and it's the second most common age-related disorder after Alzheimer's disease. And for diagnosing it, scientists had set the Unified Parkinson Disease Rating Scale, which is like the most widely applied rating instrument, and it's a range between 0 and 176, with 0 representing the healthy state and 176 with a total disability. And it's split into three main categories in rating this disease scale, from mentation, behavior, and mood for their daily activities, life activities, and their motor that's related to the movement and all their physical activity. The main challenge in this case and in the clinical diagnosis part is that patients have to be attending in clinics. And also it's a time-consuming examination that requires patient to go to the doctors or to the clinics and waiting in turn for being detected or detected by those trained medical staff. So what we are suggesting is kind of remote replication of this diagnosis process using speech tests where we can utilize those vocal measurements from patients and just predict if there is any probability for having Parkinson with their case. And our model is being trained on like pre-recorded patients' speech signal to forecast this this Parkinson probability case. Our data set was collected using the Intel at-home testing device, and it's an available data set, available online data set. So patients had recorded their vocal measurements in-house, and also it was labeled using clinical staff, labeling patients as they are having or they are not in a good health state, and it contains the recordings from 62 patients with every patient with 6 observations for the vocal measurements were 23 features, and we had like over 250 recordings. And the main features being used for detecting the Parkinson are related into the frequency, the amplitude, and the noise. So our feature space is more distributed over those speech features: the jitter, tremor, noise, RPDE, the recurrence period, density, entropy, the trended fluctuation analysis, and pitch period entropy. And all those features are related to either noise, either frequency, or amplitude analysis. What we will see in a minute using the code we're going to be working on will be importing data hosted on Snowflake for the Parkinson patients. It's stored on our Snowflake instance. We're going to apply feature scaling and train this data set and evaluate our model. So we're going to start with our code. Let me just share my screen. So we'll be importing We'll be importing in Python our Snowflake and our Snowflake connectors and Python connector to Snowflake. I've just installed those locally on my machine. So first of all, we're gonna start by making sure that we are able to connect to our Snowflake instance to pull data from it. And for this case, I'm gonna I do have my credentials stored in a JSON file. I'm gonna import them. In my credentials info. And load it. Then we're gonna use our Snowflake connector. And our account. We're gonna initiate our cursor to run the query. Then we'll test if this connector is working in the right way. We're gonna just get our current version. We're gonna fetch this result. And here is the 5.21.2. So we're able to connect to our Snowflake. Now we're gonna get our data set from the Parkinson DB. So we'll use the same. I close the initial connection just to okay. I'm gonna connect now and setting also the warehouse we will be using. So I already have in my Snowflake instance a testing warehouse created. So now we're gonna execute those queries to first of all set the role to be the sysadmin. And we're gonna query by selecting from the Parkinson table we already have. So here is the database name, the schema we're using, and the table's name. We're gonna also execute this query to be read directly into a data frame using the pd.read SQL. Connector. So now we're able to read the data from the Parkinson table. We're gonna show you a preview of this table. So here you can see it below. For every patient, those are the the vocal measurements we're using. And we have this column called status that indicates whether the patient has a Parkinson or not. So we're gonna just split our data into the feature space and do first some kind of getting the data types we have. So here we can see those are the columns the features we have. They are all numerical input, numerical features. There is no categorical other than the name, which is an object or a string. We're gonna see if we have any null value. Actually, this data is clean. It's already a clean data available where there are no null values or duplicate values. So for that, we're gonna just set our feature space, which is data here for selecting all the rows, and then we can select the feature space to be all the columns except for the status, which is the target variable we're trying to predict. We're gonna get its values. And the labels is the same as above, only by selecting, being specific about the status column. We're gonna get its values. Now we have the labels and the features aside. We're gonna show if we're gonna check for its for the distribution of the target variable we have. So the labels, we're gonna select for label equal to 1. Actually, let me just using the Seaborn library just have a counter plot for those labels. We have the zeros and the ones. Status. This should be working. So I don't know if is the screen visible to you guys? The graph, is it visible? Let me make sure I'm sharing the right, the whole view. So I believe now. So this is the figure generated by this Seaborn library, and as you can see, we're kind of equally distributed data between patients with Parkinson and the healthy ones. And now we're gonna just start fitting our data into machine learning models. We're gonna try multiple models, but before that, we're gonna do some scaling. So scaling is mainly used for like the feature scaling. Actually, it enables the model to deal with all features in an equal way, no matter what's the unit scale of it. So it's like if a certain feature is like distributed between 0 and 10,000, and another one that is spread between 100 and 200, giving it the same range to be distributed between 0 and 1 for all features, so that no feature will be overweighted compared to other feature. So that's why we're gonna use the min-max scaler and set it to be between 0 and 1, or let it be between -1 and 1 to provide more scale for having different values. We're gonna fit our x, fit transform, so it would be replaced by the same value. Our features, our features value that we got before, and the y will be equal to the labels. No need to scale labels because we are not using them directly in the model implementation, only for comparing our predictions. Let me just close this plot. So here we got our x values matrix, which is a scale between -1 and 1. And now we're gonna just do the test train split. So for that, we're gonna get the x train, x test, y train, and y test, and use the train test split from scikit-learn and apply it on the x and y with the test size split equal to 0.13. 0.2. But first, let me just import from scikit-learn the train test split function. So it exists in the model selection. We're gonna do this x test train split, and now we're gonna start just fitting our models. So we're gonna start with a logistic regression model, the simplest and less computation cost model compared to others. We're gonna just fit into the linear model from scikit-learn. We're gonna choose that logistic regression function. We're gonna set the multi-class to over with the weighted class balance. We're gonna fit our model with our training data. X train and Y train. Sorry, here we have this typo. So now after fitting our model, we're gonna also predict our unseen data by the model, the one that's the X test and the Y test. We're gonna just from the linear from the logistic, and we're gonna check for the confusion matrix, and I'm gonna talk in a bit and explain for those different metrics that are related to the accuracy, precision. Is the audio good right now? Yeah, so sorry for this disturbance. So as I was talking about the logistic regression model, we just created our logistic regression model with balanced class weight. We fitted this model with our training and with our training data. And what we are trying to do is just predicting our testing data set, the one that we got from the train test split, and we're gonna calculate its confusion matrix to see different evaluation metrics I'm gonna explain in a bit that are more into related to the accuracy, the precision, the recall, and the F1 score. So for the confusion matrix, we're gonna just use we're gonna set it to be in a data frame, which is from scikit-learn, the matrix function. Let me just so there is a function called confusion matrix. We're gonna apply it on the Y test, the unseen data by the model that was already, that's the real data actually, compared to the predicted one we got from the model we had fitted, and we get it over here from the X test. So if you can see here below, this confusion matrix indicates that we were able to predict like 0 indicating no Parkinson and 1 indicating the existence of Parkinson disease. We were able to predict 19 true negative and 27 true positive. And this enables us actually to calculate other metrics like the accuracy that I'm gonna also get them from the same function over here from the matrix function. We can utilize it to check that for the accuracy score, the same way we calculated the confusion matrix using the Y test and the predicted data. So our accuracy is 83%. We can round actually this result. And the same, using the same function, we can use it for getting our precision score. Which is 79%. And let me just get also the recall. So our recall value is 93% and F1 score is 85%. But before trying other models, I would prefer to just have a brief explanation of those evaluation metrics. So for those evaluation metrics, So we have the accuracy, which is more like the ratio of the truly predicted observation compared to the overall observations we have. And it's considered to be a good measure only if we have a kind of symmetric data sets where the distribution of data between the patients with Parkinson and the patients that are healthy are almost the same. And actually, it's a little bit. It can be kind of misleading in case we don't have this symmetricity in data. So that's why it's preferred to use those other evaluation metrics, and its equation is true positive, true positive and the true negative, which are this side and this side, compared to the overall observation we got. The other evaluation metric, the precision, which is the ratio of those correctly predicted observation compared to only the positive observations. And the question that this evaluation metric is trying to answer is like, out of those predicted Parkinson disease patients, how many are really infected? So it's comparing within the positive observation entity only, and the equation of this precision metric is the true positive compared to the true and the false positive observations. The other evaluation metric, which is the recall, it's more sensitive. It's more like answering out of all patients that were truly infected, how many was the model able to detect? So it's combining the true positive, it's evaluating the true positive predictions compared to the true positive and the false negative ones. And that's why we have, like, between the recall and the precision, we have this last evaluation metric, the F1 score, which is kind of the weighted average between those two metrics. And of course, as much as the F1 score is high, as much as it's indicating we're having a good model, being able to predict and not be kind of biased with certain prediction scale. So getting back to our code, so in the first step, we were trying to use the logistic regression, and we got those evaluation metric. The F1 score was like 85%. I'm gonna just type it down here. For the logistic regression, and using also the scikit-learn library, we're gonna run a support vector machine classifier, and the same way we did above, we're gonna use the same approach. So for the SVM model, we have already imported the SVM from the scikit-learn above, including the metrics and the linear and the confusion matrix. So the SVM model, we can just simply import the SVC function and setting the kernel to be a radial basis function, the RBF. Of course, there are many other parameters we can set for more optimized results and tuning it more, but we're gonna just fit this model with our training data. And our predictions, the same way we did with the logistic regression. We can simply just use the SVM model we initialized and just predict the X test partition using the predict function. And I'm gonna use the same snippets for getting those evaluation metrics. The only thing that would be different is this variable name. So the confusion matrix, we're gonna just set those. So remember in the logistic regression, we had an F1 score of 85%. And now here down, we can see the 81.9, approximately 82% F1 score. With the support vector machine model. We can also utilize just trying to run another model. We can check, we can get the XGB boost classifier. We're gonna set our model. But first, we're gonna just import the XGB classifier from this library, and we can just use this model directly. So we can just set this XGB classifier, and the same way we did before, we can just fit our model to this training data set we have. X-train, Y-train partition. And those are the default input values for the XGB boost classifier, and we can also get those evaluation metrics to see which one So actually the XGB boost was, as it's showing for the scores, the F1 score is 88% down here. And it had outperformed all those models we have used before. That's why we, the prediction criteria starts like in an iterative process by just trying different models. Of course, sometimes data diversity and data distribution plays an essential role in just setting which model to use. And this is actually the way you can just start with it. And any question is welcome. I'm ready to hear your questions. So I got a question from Mark by recommending the best place to learn about different machine learning algorithms and how to use them. Well, for applying machine learning algorithms, the technical side from this story, just being familiar with like Python or R for just utilizing them, practicing running different use cases. But I hugely recommend just understanding, and that's what we are planning in Data Meaning to release coming videos, short how-to videos, by understanding the intuition behind every machine learning model, so that you can more understand the nuts and bolts, how it works. and also being able to implement it in the right way, and just visualizing and showing the right results. So yeah, I prefer first of all just understanding those algorithms and the intuition behind them, and just be posted for our videos that are going to be my connection to Snowflake. I can show you this. I don't know if this was. Let me just share again my screen. So actually, my Snowflake connection. If you go actually to the official documentation by Snowflake, so for just testing your connection if it's working, so you run this query. You can simply set any credentials JSON file, your user and password you have, the same username and password you use for logging into Snowflake, and just use it through the Snowflake connector. You're welcome, Nick. So Andrew, yeah, the way Snowflake helps more in modeling our data science work actually in multiple aspects. Maybe here it wasn't 100%, we weren't able like 100% to leverage all what we can use Snowflake for, but I can just mention one of the essential things when dealing with kind of very huge data sets. First of all, importing data to local storage or reading it from an external stage with Snowflake using their architecture, it's way more faster. And also you can just have your initial data visualization or dashboards directly on premise on your Snowflake instance, which is close to where your data is being stored. And also this Python connector and the workflow, it's pipelines that can be created from Snowflake directly to your Python connector, enables you also to run it in a more efficient way for loading data and synchronizing with all changes being used. And of course, the main, as long as you can select the resources you can use for running your query for queries, you have the option to run big warehouses you can use. So this enhances more your loading and your storage workflow. So in data science, when dealing with the projects on being let's say in a production environment, so you can directly read data from Snowflake, which is, as you can see, kind of straightforward being connected, and use it directly. Is there data available publicly in Snowflake like Kaggle? If so, where can I find it? Okay. Yeah, actually in Snowflake, let me just show you my Snowflake interface so you can. Okay, so actually in Snowflake there is data marketplace well known in Snowflake, where you can explore external Snowflake. There are available data sets over there. There are free ones that you can use for just utilizing or using them for demo purposes. Let me just sign in to show you this data marketplace. Okay, so from within Snowflake, can be directed to this marketplace tab. Here you can see all type of available data set. It's the Kaggle thing within Snowflake. You can share data between different companies. Also, there are kind of private connection access. Not everything is publicly available. You can sell also data within certain submission criteria as set by Snowflake. Actually, we have used before data from Star Schema over here for COVID, I believe this one, the COVID-19, and also you can create over here dashboards. I used to have a COVID-19 over here dashboard. So yeah, I hope this answers your questions, Andrew. It's the data marketplace, the Kaggle thing for Snowflake. And actually, this is the database we were using for our DB, for our Python connector. Those are the fields and everything. So I believe I have answered on your questions.
If you have any questions or suggestions for future videos, please comment below. Don't forget to subscribe to know when future videos are posted. And thank you for watching.